Okay, nuclear stability. So you've of course have seen the periodic table, right? You have all the elements arranged, from left to right, top to bottom. You have the atomic numbers. But the one thing you haven't seen necessarily is the list of isotopes that happen to be stable for all of these elements. And there is something known as the nucleon stability chart, which shows you what particular isotopes of an element are actually stable, and where you have radioactive isotopes of the various elements in the periodic table. And so what you can see here in this graph on the right side is that the little kind of escalator looking black portion in the middle is the stable, it represents the stable isotopes of an element. The stuff in blue represents radioactive isotopes that react in a very specific manner. This is called beta emission. And then you have down here isotopes that react by another type of process known as positron emission or electron capture. Now, this type of graph gets shown often in chemistry courses. And I personally hate it because you can't see anything. You can see nothing. You can kind of see the overall picture of what's going on. And one thing that you can make up from this is that for the early portion of the periodic table, right? Because the x-axis here represents the atomic number. So for the early portion of the periodic table, you kind of have a one-to-one version of number of protons versus number of neutrons on the y-axis. But as you start increasing and you go past, like 20, roughly speaking, the amount of neutrons starts increasing compared to the number of protons. And you have kind of this skew view from that one-to-one, linear plot that you see right here. All right, now we're gonna look, we're gonna zoom in into this particular region to see specifically where the stable isotopes are. Okay, so we're gonna start with rows 1 and 2 in the periodic table to see what happens. And I'm going to basically spell out the specific isotopes that happen to be stable for rows 1 through 2. And so what you see right here are a table that increases the atomic mass going upwards, right? So you go from 1 to 2 to 3 to 4 to 6 to 7 to 9 as you go up, right? And going from left to right, you're basically increasing the atomic numbers. You go from hydrogen to helium to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, so on and so forth. All right, now the other thing is that the isotopes that you actually see present in this chart are the stable isotopes. Anything that's not actually present or that has an empty box is an isotope that would be considered radioactive, unstable in other words. And if we look at carbon-12, right, carbon-12 is actually shown present in the table, meaning that carbon-12 is stable. Okay, so we can calculate the binding energy for carbon-12. Carbon-12 is made out of 6 protons and it's made out of another 6 neutrons, right? So you have 6 protons and you have 6 neutrons with a mass of 1.00783, 1.00867 grams per mole. The mass of carbon-12 is 12.00. If we try to find the binding energy, what we basically want to do is find out what's the mass difference going from 6 hydrogens and 6 neutrons ultimately to carbon. So we will subtract the mass of carbon-12 with 6 times the mass of hydrogen plus 6 times the mass of the neutrons. And if we subtract those two masses, we're going to ultimately find out that there is a mass discrepancy of negative 0.999 grams per mole. Change that to kilograms per mole, so divide by 1,000 and multiply by the speed of light square. In other words, applying mc square equals E. To find out the energy tells us that you will actually produce 8.89, technically 8.90 trillion joules per mole of energy by simply taking the 6 protons and the 6 neutrons and jamming them together into one nucleus altogether. And this is what we call the binding energy. Okay, this is what keeps the nucleus of carbon-12 together, and that's quite a bit of energy, so that's good. And you kind of need to have a lot of energy holding the nucleus together because you have actually brought 6 particles that have the same positive charge. And you may recall from previous lectures and maybe your physics classes that like charges repel each other, and protons in a nucleus are very, very, very close to each other. So you do need a lot of energy of stability to hold that nucleus together. If that's not the case, that's when you end up with radioactive particles. All right, so moving on to the next series. So this is the third row of the elements. Here you can see sodium has only one stable isotope, magnesium has 3, aluminum has only 1, silicon has 3, phosphorus has 1, sulfur has 4, chlorine has 2, and argon has 3 different isotopes that are stable. Looking at the transition metals, the first row, you can see that there's a number of them that actually have quite a bit of stable isotopes, although there's a few that only have a single stable isotope. And pretty much what I've done right here, and I actually remember doing this, it took me a long time, probably a week, week and a half, just to do all of this. But you now can see clearly which isotopes are stable, right? Anything that I'm showing you in this diagram here on the right side of the PowerPoint is what I consider a stable isotope. Okay, and I've done it for all of them. I've done it for second row transition metals. I've done it for the fifth row and sixth row P block and S block elements. The third row, the transition metals, the lanthanides, the third row, the transition metals, and even a few of the actinides. All right, so we have a good number of things. Now, the ones that I have here highlighted in purple, they are stable enough that you can actually find them naturally on Earth, but they are still radioactive. Okay, so just be aware that these purple ones, thorium-232, uranium-235, platinum-190, those are actually radioactive. All right, so now let's take a look at the nuclear particles. All right, and we're going to follow the same format that I told you for the isotopes. We're going to have an element, except that now, in addition to elements, we're going to have particles represented by the big X. And Z is not only going to stand for the atomic number of an element, it will also stand for the charge of the particle. Okay, and if you think about it, the atomic number of the element is the number of protons, and the protons have a positive charge. So the total number of positive charge is what you're really inputting into this thing. So this actually goes hand in hand. A still stands for the mass number, so we're gonna still associate that to the mass of a nucleus. All right, one particle that you do need to be aware of is known as the alpha particle, and it's technically a helium-4 isotope, where you have 2 protons and you have 2 more neutrons, making up a atomic mass number of 4. This is known as the alpha particle. A similar type of particle, the proton, you've already seen that in a few examples already. The proton has 1 proton, since it is a proton, and the proton has a mass number of 1. You could also represent this as 1H, right? So you could just write this as hydrogen, and probably that would be the better way to do it, right? It's kind of want to make it clear that this is a proton and just a proton. Okay, there's another particle known as the beta particle, and the beta particle is simply put an electron. And the electron has a negative charge. So the number that you have here on the bottom left corner is -1. But because the electron is not something found in a nucleus, it doesn't have a mass number. So the mass number is 0. Another way to look at it is that neutrons and protons they are like 3,000 times more massive than the electron. So by comparison, the electron is basically, massless, if you want to take it to that extreme. Another particle is actually the antiparticle of the electron. This is known as the positron. And the only difference between the positron and the electron is that the positron has a positive charge as opposed to the negative charge of the electron. But other than that, it's identical. Then you have your gamma rays. Okay, so you have the Greek letter gamma. Gamma rays are simply light waves of high energy. So they don't have a charge and they don't have a mass, but they do have energy. Neutrons. Neutrons don't have a positive or negative charge, so the number on the bottom left corner is 0, but they are part of the nucleus, so every single neutron you have is going to have a mass number of 1. There's another particle that I'm going to highlight in this lecture, which is known as the neutrino. The neutrino has no mass, so the mass number is 0, and it also has no charge, so the charge excuse me, the number in the left corner is also 0. And the neutrino has its own antiparticle known as the antineutrino. And the only thing that we use to differentiate them from each other, because they don't have mass and they don't have charge, is this bar on top. Now, that's not to say that there is no experimental means to differentiating them. There actually are means to do of doing that. But, for now, we're just going to focus on writing them as either neutrino or antineutrino with the absence or presence of that bar on top of the mu symbol. Okay, so all these different particles you're going to be kind of required to remember and memorize because we're going to use them to balance nuclear reactions. And we're going to do that in the next video. So I'll stop the video right now. Get familiar with the nuclear symbols for the different particles. And in the next video, we're going to get on the actual itty-bitty details of nuclear reactions. All right, see you in the next video.